Well, greetings, mathletes, and welcome back. We're about to take our first sojourn into geometry. So this first section is introducing geometry. Geometry has always been one of the areas of mathematics that I'm very fond of. Um, it's also very, very difficult to teach. So, so this gets kind of interesting. Um, so today's lecture actually has a lot of definitions more than anything else. And the homework is really just making sure that you understand those definitions and how they work. So without any further ado, let's go ahead and get started here. And whenever we're introducing geometry, there's some things that uh, Euclid. I was trying to think of his name. Euclid was the basically our father of geometry, but he called these common notions, and these are just things that don't really have a definition, but we know what they are when we see them. And it turns out that all mathematics at some level is based on something we can't define, which is kind of interesting because it means mathematics itself is kind of a circular object, circular argument, the whole thing. Um, it's very interesting. We won't go into the philosophy of mathematics at this point, and whether it actually has a logical foundation. But just know that these are things we can kind of define them, but we cannot define them mathematically. Basically, we're going to define them by saying a whole bunch of things that they're similar to. I mean, that's essentially what we have to do. So, in any case, the first concept is a point. Oh yeah, I have to turn this thing on, right? You have a point, right? A point is a location. That's it. It's zero dimensions, right? It has zero dimensions. It has no width, no length, no nothing. Then we have a line, and a line is one dimensional, right? And it goes on, and if you're confined to, if you can move forwards and backwards on a line, that's it. Then the next thing up, this is one dimensional. If I have something two dimensional, I have a plane, right? And a plane, and this is always the drawing for a plane, but these sides extend on forever in every direction, right? So this is two dimensional. And then finally, we have space, which is three dimensional. Ooh, let's try that again. Works better when I actually have a little drag from the pencil, but we got this. Right? And I'm drawing, what do you call it? A cube, but it doesn't really have to be a cube. What we do need to understand is that these sides continue on in every direction. Oh, that needs to be this way, sorry. See if I can draw these arrows in the right way. Yeah, that should be, goes out that way. Then there's one on the other side. And then there's one that goes up, right? And then one out the bottom. And yeah, so we have these things, and then one here on the side that goes this way. So these things actually extend in three directions, right? It goes up, down, left, right, and front, back. So these things go on forever, and this is three dimensional. Three dimensions or three dimensional, right? Both are the right way to write it. Okay, now just to get a better sense of this, let's walk through these things again. But this time we're going to change our perspective. So if you've read Kafka or the Metamorphosis, you'll have a good clue of what I'm talking about here. But you'll understand it anyway. So imagine that you are a bug stuck on its back. You can't turn over. You're in one place, right? Okay, you can't move. You can't move forward, backwards, up, down, left, or right. All you can do is wave your arms around up in the air. You're confined to a point, right? Your movements have been confined to a point. Dimensions are often described as degrees of freedom. And I like that terminology because you think about the freedom to move when you talk about degrees of freedom. So at a point, you have 0 degrees of freedom because you can't move anywhere. And so you are 0 dimensional. Now, you get yourself turned over. You're upside down on your back. You get yourself turned over and you realize you're on a long string. You can move forwards on the string, you can move backwards on the string, but you can't move left and right or up and down or anything like that. You're confined to the string as far as your motions go. That's a one-dimensional direction. You have 1 degree of freedom. That's the forwards, backwards direction. So whenever we talk about a dimension, we talk about the positive and negative direction for that dimension. So being able to move forwards and backwards on the string is 1 dimension or 1 degree of freedom. Now, you fall off the string and you land on the surface of a table, right? Like something like this. Now, you can move forwards, you can walk forwards, you can walk backwards. You can also walk left and right, right? You can move both directions. So you have this degree of freedom and this degree of freedom. And I know what you're thinking. What about all these diagonal things? Well, any of those diagonal motions can be described in combination with moving forwards and moving to the side, right? So you still have 2 degrees of freedom. You have the front, back, and left, right. And so you can get to anywhere on this surface if you only move front and back and left and right. So you have 2 degrees of freedom. That makes it 2-dimensional. Now, so a point, you're a bug on its back. A line, you're a bug on a string. A plane, you're a bug on a table. Now for space, you suddenly realize you have wings, and now you can fly up and down too. So you can move forwards, backwards, left, right. So that's 2 degrees of freedom. Up, down is another degree of freedom. That's what makes it 3-dimensional. So you can move forwards, backwards, left, right, and up, down, right? So space is what fills a volume. Like your whatever room you're sitting in right now is space, right? So yeah, those are the main ideas as far as how those things work, and you can kind of see that when you go back through these drawings and look at it. You can think about, being able to be confined to a plane and then suddenly sprouting wings, being able to fly around the inside of that box. So in any case, that's how dimensions work out. Now, points. This is just naming conventions. Okay, there's different ways to name most of these things. Points we only have one way to name points. We use a capital English letter, right? So if I have a point, I can just call that point A, or I can call this point B, things like that. Okay, now a line. If I have a line, there's 2 ways to label a line. You can either label it with a lowercase script letter, like calling it line L, or you could also call it line M. I'll draw a second line here. If I have a second line here, I can call it M. That's not a script letter, right? So the convention here is to use a cursive letter, a script letter, for lines. Now, there's another way to name lines. The other way to name lines is by 2 of the points that are on them. Okay, so if I have 2 points on this line AB, I can also name this line. I don't think I'm going to get these other guys in here. I can also call it line AB, and I put arrows on both ends of that hat, right? That line over the top there is a hat, and this particular hat has 2 arrows on it. So we would say line AB, right? You could also say line BA. That's the same line. There's no difference. If I had a third letter here, say C is in between A and B, the exact same line would be AC, CB. These are all different ways to name the exact same line. A lot of the time, if you're going to be using the points that are on the line anyways for other stuff, you usually use this convention. If the line's there just to mention it and you're not really going to be using it too much in computation, usually use a script letter, right? That's the typical way to do things. Now, yeah, I think I'm just going to clear all of this off. There we go. I just need more space. Haha, that's not supposed to be a joke. Actually, this would be area, wouldn't it? On the surface here. Okay, so lines have two ways of naming them. You can either use a script English letter or name 2 points on the line with the line hat on it. Now, a plane, right? If I'm looking at a plane here, and this goes on, this goes on forever in every direction. There's a couple of conventions for this. There's actually more conventions than this, but these are the main two that you're going to see. One, planes get named with a single lowercase Greek letter. So you could call it plane alpha, right? You might want to call it plane beta. In fact, let's just go through some Greek letters just to make sure we understand what they are. So this is the Greek letter alpha. I'm just going to use the main ones that get used. This is beta, gamma. One that it doesn't get used, but we actually see it quite a lot. You see it like when you're using slope, that triangle, the Greek letter delta. In science, it means a change. I think those are the main ones that we'll see. There's a few other ones that pop up quite commonly when we're talking about naming angles. Angles are also named by Greek letters sometimes, or at least the measure of the angle. But in any case, this is the convention here. Delta is not typically used as a plane name, though. So I'm just going to cross that out, just so you know it's a Greek letter, but that's not the one we usually use for stuff. So let's go ahead and switch back here. So probably alpha, beta, and gamma are probably the main ones that you'll see. Now, the other way to name these is by naming 3 points in the plane, right? And they have to be 3 points that are not on a straight line. If they're 3 points on a line, it doesn't determine a plane. So if this is point A, this is point B, and this is point C, this would be plane ABC, right? Yeah, so it's fairly straightforward, but there are different ways of doing it, so you might see more than one as you go through this stuff. Now, with space, we're really not going to be dealing with spaces so much. If you're dealing with spaces are typically embedded in 4 dimensions. So you have a space, just like you have a plane that's embedded in a 3-dimensional space, or a point that's in 3-dimensional space. Spaces, if you're going to deal with them in terms of geometry, you have to deal with them in a higher dimension. So you end up doing things in 4 dimensions, and it's really quite, what's the word I'm looking for? Interesting. So we're really not going to have a lot of cause for that, but just know that 4 points, it takes 4 points to name a space. Yeah, and it has to be 4 points not in the same plane. And no 2 in the same plane, or in the same line. Now, we keep talking about things not being on the same line or not being on the same plane. We're going to talk about those things even more. This is basically what the how math ends up working. When you have something that you keep having to describe it as a full sentence over and over and over again, um, usually you come up with a name for it. So if 2 points points on the same line, let's put it that way, are called collinear. That makes sense. Collinear. That means with the line, they're on the same line. Okay. Points on the same plane are called coplanar. Yeah. And this one you don't have to know, but points in the same space are called cospatial. So you can kind of see a pattern here. Now, the other thing, let me get this off of here. There's also a name for points that, or for things that meet at a point. So, for example, um, here, let me just draw. Right, here's line L, and here's line M, right? And they meet at point A. Okay, so if they meet at point A, they are said to be concurrent at point A. Right? Concurrent means that they cross at a point. They both share a point. If I had a third line in here, right? This is more when you're interested about it, because any two lines that cross usually cross at a point, right? Or they're the same line. Those are your only two choices. But three lines don't always cross at the same point. So this is usually, well, I'll call this one P. This is usually when you start talking about concurrence, when you have three different lines that all meet at the same point, right? But concurrent just means they share exactly one point. Now, planes can also be concurrent, right? You can have three planes that cross at a single point. So let's take a look at that. So let's see. How do I want to? I'm going to make an attempt to draw this. Let's see how it goes. Okay, so first, let's try this here. Okay, so first I'm going to draw this plane here. Right, we'll draw that straight across. That's going to come down here. And then let's put another plane through it here. Something like that. And you can see the two, first of all, this is actually good information too. Two planes meet at a line. Let me straighten that thing out. That's driving me crazy now. Let's do it this way. There we go. Right? So we have two planes. Now, two planes cannot be concurrent because they don't share a single point. What they share is a line, right? It's that line right there. Okay, now, if we want to, let's see if I can do this here, put a third plane in here. I'll have to do a little bit of erasing here. Right, so this thing carries back this way and goes right through. Yeah, you didn't know it was going to be art class today, did you? So we'll just continue this, and that needs to go back at that angle. There we go. That's how we need to do it. There. Whew. Boy, that was a lot of work. Okay, so here we have three planes intersecting, right? That's a pretty cool drawing. Okay, and you notice the place that all three of them hit at the same time is right here. So three planes can be concurrent. They're not always concurrent, but they can be concurrent. And incidentally, when you took algebra and you were solving those 3x3 systems, what you were finding when you found a point, right? Because each of those equations was actually the equation of a plane. What you were doing is you were finding their point of concurrence. When you find a solution, that point 2, 3, -5, or whatever it happens to be when you solve the system, that's where all three planes intersect. As a matter of fact, if I go ahead and just draw these lines in here, this is extra information, by the way. What I have, is a coordinate plane, or excuse me, a coordinate space, right? The way this actually ends up, this is so extra information. I'm just getting excited. Just hang on a second here. The way we end up doing this is you picture this guy here, this plane, as your normal XY axis. So this would be your Y axis, this would be your X axis, and this would be your Z axis. And so when you're plotting things, you actually are putting it in a three-dimensional space. But unfortunately, you don't get to plot these. It's very difficult to put a three-dimensional space on paper. So considering paper is, two-dimensional. So in any case, yeah, all of this stuff can happen. You can have three concurrent planes. You can't do it with two, but you can do it with three. Okay, so let's go ahead and clear this out. Let's see. Okay, so now we want to narrow this down and pieces of lines. So let's go ahead and start with a line here. So here's a line. Yeah, so we'll just call this line L for now, and we'll put some points on here. And call this A and B. Okay, so if it just depends, oh, actually, let's give a couple more points. I'll throw a C and a D in here too. That'll give me a little help. Okay, so now what we're going to talk about are pieces of lines. So we have an entire line here, but we also have, as subsets of this line, what's called segments. Now, the segment is exactly what you think it is. It's just a piece that you cut out. It's a segment. So like the distance from A to B, this piece right here, that's a segment. The distance from C to D, this thing right here, that's a segment. D to A is a segment. D to B is a segment, and D to C is also a segment. So you have a lot of different segments in here, but they're always named by their endpoints. So if I want to talk about this segment from A to B, I would say AB, we put a hat on this one too, but we do not put arrows on the ends. Some books, and I think your book might be one of them, puts dots on the end. The main reason you put dots on the end is whether or not you're talking about what's called an open or a closed interval. If I put the dots on the end and they're closed, and right, the dots are filled in, that means that this segment includes the endpoints A and B, right? If you're using interval notation from algebra, it would be the closed brackets from A to B, right? Okay, the other way to write it would be from A to B, but with open brackets. Now, what that means is A and B are not included, right? It's only the line between A and B, but not A and B themselves. And so this would be the same as the open interval from A to B. Okay, so that's how you denote line segments. If you write this, okay, and you don't put any dots at all, it's understood to be this. It's understood to be the one with the closed dots on the end. Okay, just so we're clear. So if you see me just writing this and I don't put any kind of dot at all, that means it's closed dots on both ends. This only, well, you actually don't use these too often, right? But you should know it just because. Okay, so that's how you write segments. And it would be kind of interesting just to see how many segments we have that we can name from this group here, right? We have 4 of these things. So let's see. I have DA, that's a segment. Then I have DB, that's a segment. Then I have DC, that's a segment. Now I'm going to just move over to A and count how many segments I can make. Well, from A to D is the same as from D to A, so I don't need to go backwards anymore. I'll move forwards. So AB is a segment, and then AC is a segment. This should start to feel a little bit like the counting stuff we were doing last chapter, right? So those are all the ones that start with D. These are the ones that start with A. And now we need the ones that start with B. And if I go backwards, I'm just going to be naming stuff I've already named. So I'm just going to need to write BC here. Right? And those are all the segments that I can make with 4 collinear points. Right? It's kind of cool. But you notice how I did it. I started with D, and I listed everything that had D as an endpoint. Right? I had these 3, used all those up. Then I go to the next one, and what starts with A? Well, I can't use D because I've already used up all the D combinations. So now I just need to go through the leftover A combinations, then to the B combinations, and I just have that one, and that's the last piece. So it's just methodical counting more than anything else. Okay, now let's do this. I'm just going to clear the whole thing. I'll rewrite my line. So I had AB, and then I had C and D. Right? So I just had these 4 points. That's what I was dealing with. So we've talked about the ways to indicate segments. Okay? Now we need to talk about array. Now, array is infinite. It's not like it's not cut off like a segment is. And it's exactly what you think of as array, like a ray of the sun. What does a ray of the sun do? It starts at the sun and it beams out in one direction. That's what rays do too. You start at a point and you go on in one direction. So there's a bunch of rays in here. I have this ray from that starts at A and goes this way. I have a ray that starts at A and goes this way. I have a ray that starts at D and goes this way, a ray that starts at D and goes this way. So I have 2 directions for each one of these things, right? I can go either direction from any of the points that are named. Now, that being said, let's talk about how to name these things. Okay, so I'm going to pull out one specific ray. Let's say I want to talk about the ray that starts at A and goes off in this direction. So basically I'm looking at this, right? I have A here, and then I have a line, and I have B, C, and this thing goes on forever. So if I'm going to name this thing, the first letter that has to be written is where it starts, right? The end point. So A. Simple enough. Now, the second point you list has to be any point. It's any point that the ray passes through. So the point B it passes through and the point C it passes through. So I can name either one of those. I'm going to start with B. Okay, so this is the ray that starts at A and then shoots off forever, but it passes through B. And surprisingly enough, The notation for that is to put a ray on top of it. So you notice with the segments, we put a segment on top. With a line, we put a line on top. With a ray, we put a ray on top. So it's pretty straightforward. Now, this isn't the only way to name this though, because it does go through B. It also goes through C, right? So AC would also be a valid name for this ray, for this particular ray that goes on forever. So both of these are legitimate names as far as this goes. Okay. So this is all naming conventions more than anything else. Okay, now also when we talk about intersections and things like that, again, this is just more notation. I want black. There we go. So let's say this is line L and this is line M. Oof. Whoever made up that rule that you have to write a script letter for this, I'm not happy with them. Okay, and they cross at point P, right? Let's just say that. So the notation for this, now keep in mind, every line, it's just like algebra. Every line is a collection of an infinite number of points, right? But it's a collection, which makes it a set. So we can use some of the set notations to write this stuff. So if I wanted to say L intersects M at point P, I could say L intersects M at point P. You can actually write it this way. So when you talk about things crossing each other, you can use this intersection symbol. In fact, your book does it a bit. If two planes cross, right? We saw that before where we had planes cross at a line. So if I have two planes crossing, right, and I'm just going to do two. I'm not going to get crazy. But yeah, if I have two planes crossing like this, if this is plane alpha and this is plane gamma, then I would say alpha, oh yeah, and then the line, right? And that intersects at line L. I'd say alpha intersect gamma equals L. Okay, so that's just weird. Those are all the same symbol, just turned different directions. It's kind of funny, really. Okay, but we kind of get the idea here. It's just talking about, you can use this intersection to talk about where things cross. Now, there's also other relationships in lines. Okay, so if I have, let's see here. Well, I think most of us know what this is. Right? If I'm looking at line L and line M, L and M are coplanar. Okay, so that means they're in the same plane, which is fine because we're, it's on the same screen right now, so you can see them in the same plane. L intersect M is the empty set. That means there is no intersection. They don't cross. We want to, this is a very particular situation. If both of these things are true, then L and M are parallel. Right? Okay. Well, the symbol for that, again, this is a lot of symbols and definitions here. L is parallel to M. Right? So those two lines next to each other, they even look like parallel lines, right? This is how you write L is parallel to M. And there's some rules on parallelism. Okay, the first one is probably a little weird because it doesn't quite fit this definition, but it needs to be in place for reasons that we're not even going to use in this class, but we're going to still cover this. Um, every line is parallel to itself. Okay, this is actually called the reflexive property. Right? So you'll notice a lot of these things will feel like equality too. So that's your first property. Two, if L is parallel to M, then M is parallel to L. Now that feels like common sense, right? But it does need to be stated. And this is called the symmetric property, right? You can reverse it back and forth. So I'll put a colon here or something so you can tell that. And then the last thing is that you could pass off parallelism. If L is parallel to M and M, oops, it's hard to do that script thing, especially when you're not used to doing it. M is parallel to P, right? Then L is also parallel to P. Okay, and this is the transitive property. Right? So those are they're I call them rules, but they're properties. Every line is parallel to itself, right? If L is parallel to M, then M is parallel to L. And then the last one, basically, I'm going to throw another line in here. We'll call this one P. Basically, what it's saying is that if L is parallel to M and M is parallel to P, then L is also parallel to P. So you can pass it off like a baton, right? Notice that really does feel a lot like, let me make some space here. It feels like the properties of equality, right? A is equal to A. If A equals B, then B equals A. And the last, if A equals B and B equals C, then A equals C. If you just took the equals out and put parallel in, it would be the same properties, right? So they're almost the same thing. All right. Oop. There we go. Okay, so let's go ahead and clear this off. Control A. Delete. Okay, so geometry, you kind of expect at some point we're going to be talking about angles. So let's talk about the conventions that we use for talking about angles. So an angle is two rays joined at their starting point. Right, so here's a ray. We'll call this ray AB. And here's another ray. And let's put this point C here. So I have two rays. The place where they're joined is called the vertex. And these rays are either called sides. Wait, there was another name. Yeah, we'll just go with sides. Right? So, edges, that's the other. Sometimes they're called edges. Usually, we'll just be calling them sides, but I just wanted to make sure you saw that too. Anyways, so you have a vertex and then you have two edges. That's basically what you're looking at. The way we name it is the vertex always goes in the middle. So this angle could be either angle BAC or angle CAB. Both are valid names for this angle, right? If I'm going to be talking about the degree measure, right, how many degrees it is or something, what I say is the measure of angle BAC is equal to 40 degrees, or whatever it happens to be. I'm just pulling out a number, from wherever, just as an example, so we could set it equal to a number. So yeah, the vertex is always the middle letter when you write this. Okay, so that's not too bad. That's just, nomenclature, how to name things. All right, so let's look at some types of angles here. Okay, so some of these you guys already know. So one of these days I'm going to have this pen figured out. So if I have an angle, and I'm going to shorten this. The other thing that happens here too is that angles often get called by Greek letters. So that is the same as with planes, but the context tells you which one you're talking about. So if this measure is alpha, this is an acute angle if alpha is less than 90 degrees. Right? So smaller than 90 degrees, it's an acute angle. It's an adorable angle, let's be honest. Okay. Now, then there's also the right angle, right? I'll call this alpha still. Right angles are denoted by putting a little square in that corner. So you can actually make a little rectangle there in the corner. This is a right angle. And this is when alpha is equal to 90 degrees. And then I'm sure you've already figured out the third case, right? If that's alpha degrees, and this is obtuse if alpha is greater than 90 degrees. Now, all angles, all of them, oh yeah, and there's one more. We have to define this as a straight angle. A straight angle, right, like this, a straight angle is when alpha is equal to 180 degrees. It's basically two rays joined at the butt, pointed opposite directions, right? So it's 180 degrees. All angles alpha have a measure such that, alpha falls within 0 and 180 degrees. In some cases, you can actually consider a 0-degree angle an angle also. It's really a ray, but there are cases where it's okay to do so. So all angles fall between 0 and 180 degrees. So I know what the question is here. Let me go ahead and get this off of here. So if all angles fall within 0 and 180 degrees, what happens if I measure an angle like this all the way around, and that's alpha? Well, we don't really call that the angle. We still call this the angle. So this is your angle. Alpha is a reflex angle, right? It's the other side of the angle. You can always find a reflex angle. You can always find a reflex angle by subtracting alpha from 360. Is the measure I'm gonna relabel this. Doggone it! I still wrote this. I'm having issues. Okay, it's 360 degrees minus alpha. There we go. That's what I was trying to say. And that would make this alpha and this 360 minus alpha, right? So that, because the whole thing has to add up to 360 together. So 360 minus alpha is a reflex angle. So it always ends up being that. Yeah, so I think we got most of the main angle stuff down now. Yeah, and then the last thing I really wanted to talk about here, although it's not really the last thing, there's a lot of things. Let's go ahead and put things into context here. Okay, so let's say I have a cube. I'm just going to draw a cube here. So I'm trying to make it a good drawing, so be patient. Okay, so let's give these corners some names. B, C, D, E, F, G, and H. Okay, so we got bunches of stuff here, and then I'm going to add something else here. I'm going to add this line from A to C. Right, so that line, this line is behind everything. That one runs across the top there, and then we'll put a line here from C to F. Okay, so we can take a look at some things here. So first of all, you're going to be asked to take a diagram like this and identify things in it. So, find a couple pairs of parallel lines. Well, looking at this, any sides of a square, we already know that, every face of this is a square. Opposite sides of squares are parallel. So that means, like, you can say, oh, AB, segment AB is parallel to segment DC. Let's see what else we got in here. Oh, segment AE is parallel, you can see, to segment CG, right? They don't have to be next to each other. Let's see here. Yeah, we have perpendicular lines, right? We have right angles. Angle, if you're asked to find all a few right angles, you just find them. EAD, right? That's this angle here. Angle EFD, right? That's this angle right here. Those are both right angles. So now there's one other thing we haven't talked about. It has to do with parallelism, but it's not true parallelism. And it's the idea of a skew line. Okay, so skew lines are lines that don't intersect, right? If M and L are skew, M intersect L is empty. But M and L M and L are non-coplanar, right? So they can't be put in the same plane. Now, that doesn't mean that they have to be drawn in the same plane to be coplanar, right? Um, there are things that are coplanar. There are lines that are coplanar that aren't drawn in the same plane. For example, AB is coplanar with FG because if I cut in diagonally with a plane, I can intersect both of those lines and contain them both within the plane. However, let me just switch colors here so it stands out a little more. If I look at line AB, right, which is right here, right, or segment AB, and DF, right? Those cannot be contained in the same. Those cannot be contained in the same plane. Once you get a plane for one, the other one's going to intersect it at a right angle most of the time. So you can't get both lines in the same plane. So these two are skew, right? Those are skew lines. I know, it looks like we skewed it all up, doesn't it? Okay, so that's actually one of the big new concepts here is the idea of skew lines. They really are some of those things that it's hard to picture them sometimes. So that takes a little bit of experience to get a handle on that. It takes some practice. Okay. Now, the other thing, notice, oh, I erased the name of point A. There we go. Put it back. Let's see, where was I? Skew lines, we had some of the other main things you may have to notice are lines that are concurrent. For example, line AC or segment AC, which is right here, goes across the top. Segment FC, right here. Segment DC, where'd DC go? DC's right here. Segment GC are all concurrent at point C. In fact, you can kind of see it just from looking at this. You notice they all have a C in them. Every one of them has C. So if they all have C, that has to be the point in common. But these guys are all concurrent at C because that's where they meet, is right there at C. Okay, so those are some of the types of things that you're going to have to do. So it's about understanding the definitions and being able to draw information out of these pictures and situations because you understand the definitions. So it can get kind of technical. It's kind of interesting, but nonetheless, we are going to split this into two lectures. So the next lecture will be next week. And we'll cover the second half of this section, which is a little more mechanical in that there's more computation and things like that involved in it. In any case, this concludes this lecture. So until next time, keep your pencils and your wits sharp.